In the next part of Chapter 13, we're going to be looking at the quantitative aspect of solutions, in particular the calculation of a mass percent and a molarity for solution concentration. Okay, so these are two different ways to express the amount of solute in a solvent for a solution. Mass percent is simply the number of grams of solute per 100 grams of total solution. Okay, so solute per solution, not solvent. A solution that has a concentration of 14% by mass means that you have 14 grams of that solute for every 100 grams of the solution. So the calculation is very simple. You simply divide the mass of the solute by the total mass of the solution, which is just the mass of the solute and solvent added together, and then of course multiply by 100 to make it a percent. Note that in the denominator here, it's the mass of solution, not just the solvent, so you have to add those together. And there are different ways to express mass percent, actually. So when we say mass percent, that's per 100. Okay, so that's parts per 100. We use a percent symbol for that. But you may also see people express it as parts per million. So it's the number of grams of solute for every 1 million grams of solution, or the parts per billion. So the number of grams of solute per 1 billion grams of solution. There's nothing that says we have to use per 100 or percent. So if you have ever seen the terms parts per million or parts per billion, that's simply an expression of the mass percent of the solution. It's a variation on mass percent. Now, how can we use this to our advantage? Well, we can use the mass percent of a solution as a conversion factor. Woohoo! So we've got another conversion factor. We love those in chemistry because that allows us to get from point A to point B to point Z by using those conversion factors. So the key to using a mass percent as a conversion factor is to think of it in terms of its fraction rather than a mass percent. Mass percent is grams of solute per 100 grams of solution. So if I'm told that I have a 28% solution of glucose, okay, that is telling me that I can write my conversion factor as 28 grams of glucose for every 100 grams of whatever my solution is. If I have sugar water, let's say, using the glucose. Okay, 28 grams of solid glucose sugar put into 100 grams of solution. Okay, don't just say solvent or water. It's got to be the solution. So let's look at an example of that going back to our Lake Nyos. The water sample taken from the bottom of Lake Nyos contained 8.5% carbon dioxide by mass. So what we want to know is how much carbon dioxide in grams is that if I took a sample that was 28.6 liters of water. All right, so if I look at my given information, I know that I have 8.5% carbon dioxide by mass, okay, which in the next slide it'll show you this, but we can go ahead and just think of that in terms of our conversion factor. That's 8.5 grams of carbon dioxide for every 100 grams of the water solution, of lake water. Okay, and I took 28.6 liters of that solution. That was the total amount that I had. Now the other thing that I will need to know is how dense is that water. Pure water at room temperature and standard pressure is 1 gram per milliliter, but things vary. So the density of this lake water happened to be 1.03 grams per milliliter. Now, one thing that you'll need to remember, because notice we've got liters of solution, but density is in milliliters, so we need to recall the relationship between milliliters and liters, which is 1,000 milliliters in a liter. That information will then allow us to find what we're looking for, which is the number of grams of carbon dioxide. So if I start with the liters of solution and use my conversion factor here to convert to milliliters of solution, I can then use the density of that solution, okay, grams per milliliter, to get the number of grams of total solution. Now, if I know the grams of solution or lake water that I have, I can then use my percent, my 8.5% conversion factor to find the grams of carbon dioxide. So I plug everything in. There's the 28.6 liters that I started with. I convert to milliliters right here. Then I convert to grams right here. And then I go from grams of lake water solution to grams of CO2. And I find that I will have 2,500 grams of CO2 in that 28.6 liters of lake water. Now, another case that is shown in the book, one of the chemistry environment boxes, talks about fat-soluble POPs, persistent organic pollutants. There are a number of chemicals that are potentially harmful to us as human beings and to other living species that can make their way into water sources from a variety of places, from industries that are dumping these chemicals knowingly or unknowingly, from spills that happen, atmospheric emissions, runoff from agriculture, so the application of pesticides and herbicides and fertilizer, dumping of household waste. All of these things allow potentially persistent and harmful organic chemicals to make their way into our water sources. And since not only do we rely on that water, but then other things that living species that rely on them that we also rely on, such as crops, livestock, and fish, we're all dependent on that water source. All of these living species can accumulate these chemicals from the water. And then we as humans consume the livestock, the fish, the crops that are grown with these contaminated sources of water, and we start to build up a higher number of these potentially harmful chemicals, which leads to a number of diseases or health effects, such as an increased risk of cancer, liver damage, central nervous system damage, mutations. There are all sorts of things that go along with that. So not only our country, but countries all over the world, the governments have kind of gotten together to try to ban the most egregious of these chemicals, these persistent organic pollutants that are not only harmful, but don't tend to break down very quickly, so they remain in the environment for a very long time. Now, the original treaty created by these countries targeted 12 of these substances, and they're known as the Dirty Dozen. So if we look at those, it'll be in the next slide. The Dirty Dozen really are the ones that we want to focus on. They're the POPs. Once they get into the environment, these POPs don't break down. They stay around for a long time, and then they can also undergo what is known as bioamplification, which means that because they're nonpolar, they don't tend to break down in the aqueous parts of a living system, be it animal, vegetable, or human. But they get stored, and we're talking about living organisms here, they get stored and concentrated in fatty tissues for the organisms that consume them. And then if you go down the food chain, that larger organisms eat smaller ones. The smaller ones have consumed the chemical, it got stored in their fatty tissues, then the larger one gets a big hit that's all concentrated in the fatty tissue, and then it gets stored in their fatty tissue, and it's sort of an exponential effect. So you see kind of an exponential increase in the concentration of the chemicals as you move up the food chain until you get to that ultimate, top of the food chain, which tends to be us. So the Dirty Dozen are listed here, and they're in your book in Table 13.3, so you can see what those are. You may be familiar with some of those. We're not going to go through them individually, but there they are. Now, in the U.S. at least, the presence of these contaminants in a water supply is monitored through the EPA. And the EPA has set what they call maximum contaminant levels for each of these 12 compounds in the Dirty Dozen. So there's a certain level that can be found in food or drinking water. And here's just some examples of that. So the chlordane, you cannot have more than 0.002 milligrams per liter of whatever food or water source you're looking at. Dioxin, look how low that is. Dioxin is very dangerous to us, and it's a dangerous toxin to have built up, so much, much lower level there. Heptachlor, hexachlorobenzene, these are things that you want to keep at very low levels, Okay, and it's important because of the amount of those in solution. What is that mass percent that you're allowed to have in there? All right, now mass percent is one way to look at the concentration of something, but again, it's based on masses. And as you know by now, in chemistry, we don't like to necessarily deal with masses in the lab. I mean, we deal with masses because that's what we can measure, but we want to think of things in terms of the number of units, not in terms of their mass, because mass is not comparative. It's not apples to apples. The mass of one compound may not relate to the mass of another, and we want to be able to relate compounds one to the other. So we need a way to specify solution concentration based on number of particles rather than mass of particles. And that's where this term comes in, the molarity of a solution. Okay, so molarity, which is abbreviated with the capital letter M, is defined as the number of moles of solute per liter of solution. Okay, so it's similar to what we saw for mass percent, but instead of grams of solute, we look at moles of solute, and then instead of grams of solution, it's liters, volume of solution. So number of particles per volume of solution. Okay, and again, notice that that denominator is the number, it's the amount of solution, not solvent. We're not using solvent anywhere for mass percent or molarity by itself. Okay, it gets lumped in with the solution. All right, so how do we then make a solution of a particular molarity? Well, what we're going to need to do is use molar mass to convert from the number of particles we need to the mass and weigh that out. So you put solute into a flask, a volumetric flask with a very specific volume, and then you add water up to the desired volume. So here's a figure that's out of your book that shows how to prepare a 1 molar sodium chloride solution. So remember, if you calculate molar mass of sodium chloride, sodium on the periodic table 22.99, chlorine 35.45, you add them together, 58.44 grams in 1 mole of sodium chloride. So you weigh that out, that's 1.00 moles of sodium chloride, and you add that to your container, okay, volumetric flask that's designed to hold exactly 1 liter of solution. Okay, so this is a 1 liter volumetric flask. I'm sorry, that first one's supposed to be a 1. Again, a little bit hard to write on the screen. Now you add deionized water until the solid dissolves. So you add just enough to the bottom, swirl that around and let it dissolve, and then you continue adding additional water until the meniscus is on that mark, that 1 liter line that we have in there. You put the lid on and you mix it thoroughly to make a homogeneous solution. That gives you a 1 molar sodium chloride solution. Okay. What you don't do, you do that, you don't put a tooth in water. But again, another corny chemistry joke. What is a tooth in a glass of water? It's a 1 molar solution. So there you go. 2 ways to make a 1 molar solution. The one on the left is the preferred method. So how can we carry out our calculations with molarity? Let's say that I took 15.5 grams of sodium chloride, poured it in a beaker, and then added water to make exactly 1.50 liters of sodium chloride solution. And let's say we've got much better beakers than we have in the lab because we can measure precisely 1.5 liters in this beaker. Normally you would need a volumetric piece of glassware. All right, so we know that we have 15.5 grams of sodium chloride, 1.5 liters of solution. Okay, it's very important. They didn't say that they added 1.5 liters of water. That's the total volume of solution. We want to use that to find the molarity. Okay, so what we need is the moles of solute. Okay, we've got grams, so we're going to have to convert that to moles. And we need the volume of solution, which we have. Okay, in liters, and that has to be in liters too. Remember, we don't want milliliters for molarity, liters. So all we need to do is figure out how many moles of sodium chloride we have. So we take our 15.5 grams and our molar mass and convert it. So we find that we have 0.2652 moles of sodium chloride. Now notice here what they're doing with this number. According to significant figures, 15.5 would limit us to 3. But we want to avoid rounding errors. Normally, You could just put this whole calculation into your calculator and then round it off at the end. That will avoid rounding errors. But what we're going to be looking at here is, carrying this one piece down into the next step. We want to avoid rounding errors. So even though we would normally round it off to 0.265, we're going to carry one extra digit to help avoid those rounding errors. So we just underline the 5 to indicate that's the level of significant figures, and then we carry the 2. Okay, then we bring it down here and plug it in for moles of solute. Here's the liters of solution that we were given, and we discover that we have a 0.177 molar solution. So now when you go in the lab and you pick up bottles that are labeled as, 3M acid, that is a 3 molar acid solution. It's telling you there are 3 moles of that acid for every liter of solution. Okay, so it can start to tie in then to the masses that you have. Here's another example. Let's determine how many grams of sucrose, which is C12H22O11, that we would have in 1.72 liters of a 0.758 molar sucrose solution. Okay, so when we look at this one, we're trying to find how many grams. And there's nothing in here with grams, but we do have moles from right here, because what this is telling us is that we have 0.758 moles of the sucrose. That is supposed to be a 0 there. I am so sorry this is written so poorly. The screen is not picking up the touch screen very well. Okay, so 0.758 moles of sucrose, and that is per every 1 liter of solution. Okay, and then we know how many liters of solution we have. Okay, so they told us that was the sucrose solution. So if I combine liters of solution with moles per liter, that allows me to find the number of moles of sucrose, and then I can get to grams. So I start with liters of solution, use molarity to find moles of sucrose, and then I need the molar mass of sucrose, which they've kindly calculated for us here, but you can do that. It's just, carbon 12.01 times 12, hydrogen 1.01 times 22, oxygen is 16 times 11. Add that together, 342.34 grams, and then I can get to grams of sucrose that are here. Okay, so they just kind of have highlighted the relationships used here. Okay, and then we plug it in. So when we do that, notice right here, this is our molarity. So what you've got to be able to do is start translating in your mind whenever you see a molarity, you see a capital M, think of it in terms of the number of moles per 1 liter of solution. So just like with molar mass, when you see a molar mass, it's the number of grams in 1 mole. Molarity is always the number of moles of something in 1 liter. Okay, so it's always 1 with the liter in this case, and the moles will vary for molarity. So we calculated our number of moles in the first step, and then we calculated the number of grams in the second step. We find out that there are 446 grams of sucrose in that particular solution that we have. Now, when we look at molarity, something that ties in with that is the idea of an ion concentration. So instead of looking at the concentration of the entire compound that you put in, you may want to know just what was the concentration of ions. The reported concentration of a solution of a molecular compound reflects the concentration of that solute as it actually is. So the sucrose example that we just did, that is the real concentration. That's really what it would be. If you had a 1 molar glucose solution, you would have 1 mole of glucose for every liter of solution. But now it's a little bit different for the case of an ionic compound. If you report the concentration of a solution containing an ionic compound, that is reflecting the concentration of the solute before you dissolve it in solution. And I know that sounds weird, but it depends on how many ions you produce when you put it in solution. So for example, if you have a 1 molar solution of calcium chloride, even though it's 1 mole of calcium chloride per 1 liter of solution, Calcium chloride doesn't really exist once you put it in water. It's soluble. It's going to break apart into ions, and it's going to form one calcium ion, okay, for every unit, and then 2 chloride ions. So when you look at the concentration, the number of moles of ions, there's 1 mole of calcium per liter, 2 moles of chloride per liter. So the concentration of chloride in that solution is twice the concentration of calcium. So the concentration of individual ions that are present in a solution can be approximated from the overall concentration. You just have to multiply by the number of ions that you will produce in solution. And that's important to keep in mind because sometimes, especially with electrolyte solutions, if you're dealing with, say, a medical scenario where you're trying to give someone an electrolyte solution, if you want them to have a particular concentration of, let's say, in this case, if for whatever reason they needed a particular concentration of chloride ions being delivered, then if you were trying to give them 1 mole of chloride ions and you gave them a 1 molar calcium chloride solution, you're actually giving them twice the amount of chloride ions you were intending. Okay, not that you would be giving people chloride ions, but just as an example. So you have to be careful with that ion concentration effect. Okay. Now, we say that we approximate it, we multiply by the number of ions. The reason it's an approximation is because when you dissolve an ionic compound in solution, sometimes some of the cations and anions might pair up and bind together so they're not actually ions. The actual concentration of ions are generally a little bit lower than what we approximate, but the approximation will work just fine for us. Let's say we want to determine the molar concentration of sodium ions and phosphate ions in a 1.5 molar solution of sodium phosphate. All right, so here's what we're given. Concentration of sodium phosphate. I want to know the molarity not of sodium phosphate, but of each of the individual ions. So all I need to do is take the molarity of the solution, and I do not know why that just happened, take the molarity of the solution and multiply it by the number of ions here. So since it's Na3PO4, I'm going to multiply the concentration times 3 to find the molarity of sodium. It's about 4.5 molar. Phosphate, there's only 1 of those in here, so I just multiply by 1. So I still get the 1.50 molar. Okay, so the concentration of phosphate would be the same as the concentration of the entire solution, but the concentration of sodium is 3 times that of what we started with the sodium phosphate. All right, so those are some examples with molarity. That is a very, very brief overview of molarity. There's so much more we're going to see and do with molarity. So again, be sure you get comfortable with that. Work plenty of problems dealing with molarity. Inscribe it on your brain. You're going to be seeing molarity from here on out.